Hello and welcome to our lesson on using a catalyst. So we've discussed there are 5 things we can do to change the rate of reaction. With all of these, if you increase them, they will increase the rate of reaction. And if you decrease them, you will decrease the rate of reaction. The one exception to this is the catalyst. It's not about increasing or decreasing. It's about if I have one or if I don't have one. Okay, so let's move on and find out about a catalyst. Okay, so the first thing we need to remember is catalysts are any substance that speed up a reaction without being used up themselves. Now that second bit is going to be crucial. It pops up a lot in the exams. Okay, so the 2 points to catalyst: it speeds up a reaction and it isn't used up. So it should look the same at the end of reaction as it does at the beginning. There are different catalysts. Often transition metals, those metals between group 2 and group 3, are often used as catalysts. There are others, but they're the main ones. But different catalysts are used in different reactions. So it might be hydrogenation uses a nickel catalyst and cracking uses an aluminium catalyst. But different reactions have different catalysts. Not all reactions have a catalyst that works. So some reactions we can't use catalysts simply because we haven't found one that works yet. The last little bit then here is that we only need a small amount of a catalyst to affect a large amount of reactant. So because we only need a small amount and because we can reuse them because they're not being used up, it makes them very economically efficient. So in an industrial process, if you're trying to make a lot of product because you want to sell, rather than increasing the temperature or increasing the pressure, that takes a lot of energy, a lot of money. You could just add a little bit of catalyst. It could be expensive because often something like platinum is a very expensive catalyst, but because it lasts a long time, because you only need a small amount, it's actually worthwhile financially to do that. The catalyst side of things ties in with this idea that we've learned about with energetics, endothermic, exothermic reactions. We know the activation energy needed to start that reaction. We need that minimum amount of energy needed for the successful collisions to occur. So starting that reaction, getting those successful collisions actually happening. Now you should remember from endothermic, exothermic reactions that a catalyst doesn't increase the number of collisions overall. It doesn't increase the amount of products made. It simply works by making those collisions more successful. And the way it does that is by providing an alternative pathway that doesn't need as much activation energy. And so collisions occur more successfully with less energy needed. Now, don't worry about the details of this slide. It's just really the gift that I wanted you to look at. So you'll notice here the surface of the catalyst, so this might be a transition metal, is attracting the reactants. So they're all wanting to come towards this catalyst. It's a bit like having an ice cream van at the end of school. Rather than spreading out, you guys all kind of go towards the ice cream van, don't you? And you're more likely to collide with each other. And that's exactly what's happening here. All the reactants are attracted to the surface of the catalyst, and so they move closer together and therefore are more likely to bump into each other, to collide successfully and cause that reaction. And it's taking less energy because they're just naturally gravitating towards the surface of the catalyst. So a typical question about catalysts: how do you know something is a catalyst? What would you be looking for in a catalyst? So you might say, well, think about what a catalyst is. You would expect a reaction to speed up and you would expect to have it looking the same as it was at the beginning. What would you be looking for? A faster reaction. How do I know if something is a catalyst? So remember I said certain catalysts work for certain reactions. So in this example here, I have hydrogenation. I've got some powdered nickel. How do I know if that nickel is going to act as a catalyst for hydrogenation? Well, if I just put the powdered nickel in and the reaction happens, how do I know if that nickel's actually acted as a catalyst? Well, I need kind of a before and after, don't I? I need without the powdered nickel and with powdered nickel. And if the reaction is faster, then I know that the nickel is acting as a catalyst. Obviously, I would also need the nickel to still appear as nickel at the end. So this is similar to a question that came up a couple of years ago on an exam, and the question was, which of these is a catalyst? And a lot of people chose, where is it? So here you can see I've got nothing here. So this is what I'm comparing it to. So without anything, it took 300 seconds for this reaction to happen. This one obviously is not right because it's the same amount of time. And a lot of people chose this one because it had gone down, and I don't know whether they recognise the name or whatever. So they said, well, the copper oxide is the catalyst because the time taken has gone down. And they were wrong, because the other part of a catalyst is it remains the same. It isn't used up. And you can see here, copper oxide starts as a black powder and ends up as a blue liquid. So it's actually been part of the reaction. It's made something new. So copper oxide is not the catalyst. It's actually the copper, because it also decreases the time taken, but you'll notice it stays the same. And that was the bit that caught a lot of people out. Okay, so hopefully those examples have helped you. Okay, that's the end of this lesson, guys. I'll see you next time.